Hi, this is David. Welcome to Part 1, Topic 2, Miller's Chapter 5, which concerns hypothesis testing. As usual, there's a workbook associated. It's labeled T2.8.5, so that's Reading 8 in Topic 2, and the Dot 5 indicates Chapter 5 for Miller. There are several sheets or worksheets inside the workbook, none of which I've tagged as highly relevant if your goal is just to pass the exam, but we've got illustration of the confidence interval, the so-called sampling distributions. So that's primarily test of sample mean, test of sample variance, and also comparison of two variances. But the comparison of two variances will be very low testability. We have students' T lookup table and then Chebyshev's inequality. So let's take a look here. It starts with asking us about the mean and variance of the sample mean. And so this can be a difficult idea at first glance because the key here is we're treating the sample mean like a random variable. You really have to start with that idea. Understand, each time we draw a sample, we take the mean, we do it again, we expect each time to get a slightly different sample mean. So that sample mean itself can be characterized as a random variable. And then we see here that the variance of the sampling distribution of means is given here, which is the variance of the population divided by n. So you'll notice this value here, or this estimate, will decrease, tend towards 0 in fact, as n increases. So can be counterintuitive. It's saying that the variance of the sample mean is equal to the population variance divided by the sample size. How can that tend to 0? Well, because as the sample gets larger and larger, it starts to approximate the population itself, and there won't be as much dispersion in the sample mean. We just have to keep in mind that the sample mean is a random variable itself. So that variance that we just looked at, if we take the square root of it, we get, as you would expect, a standard deviation. And the standard deviation happens to be called the standard error. So the standard error is just another standard deviation that happens to be of the sampling distribution of the estimator in this case, which is the sample mean. And so if a population is distributed with mean of mu and variance of sigma squared, and by the way, we have these Greek symbols which connote population population parameters as opposed to sample statistics, then the standardized variable given by z is asymptotically normal or approximates normal increasingly as n approaches infinity. So here's that variable here, and we'll use that often. Right in the numerator, it's just the distance between, notice the difference here, Roman and Greek. The observed sample mean, that's the sample mean we happen to observe in this sample. It's going to vary each time we go to draw a sample. Difference between that and what we hypothesize to be the population mean. So that's a distance, and then we just standardize it by dividing by, what is this in the denominator? The standard error. That by standardizing it, then we get a variable that we can say is asymptotically normal. Normal with mean of 0, variance of 1.